Yeah, this is going to be a really quick introduction or information only what we call about system or process dynamics. I said dynamics in a process that we want to control. How is the process reacting? You know, can it store energy or doesn't it store energy? Get the energy back. Let's say I store energy and then I get the energy returned. So it seems like I'm getting more out of the system than I put into it, and so on. But this is just quick for information. So system process. What we have here is a system or process that we maybe want to control, or usually what we do in automation is we control it. So we add energy or mass to our process and we get out energy or mass out of the process. And the state of the process, dynamic flow of mass energy in the system. That's the dynamic. And what causes the dynamics is system inertia. We are pushing the system, but it's kind of reluctant. I don't want this, but eventually I have to get it. And I don't get it. And when I get it, okay, I'm going to hand it out later on, but you have to wait a little to get it. So this is the system dynamics. And then we have losses too. If I put more mass into a system, now get more mass out of a system than I put into, or more energy out of the system than I put into it, that's usually not the case. For energy, of course, if this is a chemical process that generates energy, of course I will get more energy out of it than I put into it. So that's the system dynamics. And here is this phase and gain that we are always talking about when we talking about systems. Okay, the gain is that this is what I put in and this is what I get in, and the gain is the ratio between what I get out and what I put in. So that is it. And then we call about the phase, which is caused by this inertia. I put it in time zero, and I can't kind of register what something out of, I can't register the effect of what I put in because the system is kind of reluctant. I don't want this, I don't want this. But eventually the system has to get it and then has to hand it back out. It's going to take some time. And the phase itself is related to, I use a sinusoid into the system, and how much is this lagging for a phase here. 180 degrees, which would be this one, that's 360. What portion is this time lag here of this 180 degrees? So it's the time here, the TF and times 180, and then you get it in degrees. And if you look at this, is this TD here is not going to change. The system isn't going to be reluctant all the time. But if you increase the speed of the input, of course, this phase is going to tend towards minus 180. So if you decrease the speed, of course, this TD is going to be a small portion of the TF, and this one is going to be a smaller number. And it's usually too here with the gain too. The higher the frequency, the lower the gain. Because I put energy into the system is reluctant, not outputting anything, and then I remove the energy again. Oh, okay, so I don't have anything to output. So for really high frequency, maybe the output is 0, because I'm giving you something, but I'm just taking it back. Sorry, you can't have it. And then these systems, this stuff, they are differential equations. You can like it or not. And what we can do is we have a time function. We have a function in time domain with some input, then we get some out of it. And then we need to do a convolution because the input is passing through the system, and as you pass through the system here and getting modified, what do I get out here? So it has to do with multiplication and stuff. It's tough. It's tough. So what they did, or what Mr. Laplace did, is that I need an easy way to solve differential equation. So what I want to do is I want to transform this time domain into my new domain, frequency domain, where I can use normal algebra for differentiation and integration. Kind of nice. So I don't have to do this stuff. And then I go here, do my algebra and solve this. My input function looks like this. System looks like this. I multiply this stuff here. And then I do an inverse back. And then I'm back in the time plane, because we are not working in the frequency domain. We are working in the time domain as the time progresses over fourth dimension. So that was he wanted to do. Basically what it does, he says, okay, all the solutions they get to this differential equation and multiply my function with that, and let's check out those who end up with 0 is not a solution, those who end up with a number is a solution to this stuff too. And it's also related to what we call Fourier transform too. In Fourier transform, this part here is 1. We say that, okay, the sigma is 0 too. So that's just us. Fourier transform is one special case in one plane of the Laplace transformation. And then we have some Laplace transformation pairs dependent on the input function. Here are some input function. We use a sign a lot. And steps, unit step, like that. Unit step is a pure integration. Because if I put a unit step into it, I transfer energy into my system, and the energy in the system is going to increase on the input. Of course, it's going to output energy too, but from the input side, it just looks like an integrator. Yeah, and unit input is kind of nice, because if I test it with a unit input, then it's, we go back here. Basically, there's a 1 in here, so it's just this one I'm looking for, and that's the one I am looking for often. So, but the unit input is let's see, the A here is not the A goes to infinity, the A goes to 0, and this A here goes to infinity. So I also vision, so the A goes to infinity. Come on. And of course, this duration here goes to 0. And then we use tables. So here, input, and then we do calculation, and if we get something looking like this, this will be the time function. And we, or better, of course, we will use MATLAB for doing this for us now. We are in 2024, or Python scripts or whatever. We can get hold of our Python library doing this for us. And then we have to analyze these systems to see what is it doing for us, and then what kind of system do we have. And one we can do is a step response. We put a step into here. We have inertia. And we might also have a transport delay here. It takes some time for my energy to reach my system, and then we have inertia. I'm reluctant. I don't want to do anything, but I have to do anything. And then I have a loss. Here it doesn't seem like I have a loss. I put 1 into it and I got 1 out to it, but it doesn't need to be the case. That was first order. And higher order systems, they have oscillation tendency. Dependent upon, there's a formula here, it depends upon damping and so on, but you can get this stuff. I put something into the system, and this is something I put into a tank, and here I'm overflowing. Not too bad. So a first order system, okay, we can handle those. A second order system, we have to be a little more careful. System analysis. So this is step response. Let's say, do I get something like this? And then we have the frequency response. This for first order. We have put all frequency in here and see how does my system react to all systems. And then is Y, a real system. What I put into a real system is not a sinusoid when I'm controlling it, but a signal I put in potentially contains all frequencies as sinusoids, because it is a signal. But what I do check here, I say this system is going to work for all frequencies, so whatever I put into, what signal I put in or stimulate my system with, is containing all the frequencies, whatever, but I have tested it works for all frequencies, so I'm good to go. So it's a mathematical analysis, but you can do practical tests too. If you want to test this, you can test a few frequency if you assign generate, put it into the system, get a few points there and say, yeah, okay, this looks like a first order system, nice. And they tend to be stable. But then again, we have a second order higher system where the system can store power. Then there's a different baby. So what we are looking for is the, let's say, counter phase here, the 180-degree crossing. Let's say down here somewhere, 180 degree here. I want to stay away from that, because that is for that point, or the gain has to be low than dependent. But what is happening here too is, at that case, I'm putting energy into the system when I really should remove energy in opposite phase. You can look at driving a car on a hilly road. What you're doing, there's full pedal downhill and no pedal upstream. So full throttle down, no throttle up. And of course, this system is going to be unstable. So if you go back here to this one, this is going to just oscillate because you are sitting here with a frequency on here. Full pedal downhill, no pedal uphill, and you know it's going to speed up, slow down, speed up, slow down. It's not going to be nice, and that's probably not the way you want to drive either. And that's not the way you want to control the system. So you want to stay away from this one. And if you are down here, the gain has to be low at least. So I'm not okay. I'm pedaling downhill, or I have a throttle down here, but not much. And when I go uphill, okay, yeah, I have a little throttle at least when I go uphill too. So it's not oscillating that hard. And then we have also, this is Laplace the way, but then we can also solve differential equation using a state space model. And that usually we use for multiple input-output systems. And then we have got these matrices. Here are the differential equations, and that can be discrete, or we can say that the derivative is the Euler first order. A couple of samples divided by my sampling time, and I end up with these discrete, and I can solve this using MATLAB, CLab, Python, or I can program this in a PLC if I want to. I wouldn't recommend it, but you can do it. And here is something you can do. So that's state space model. And in modern control, I say MPC control. That's usually a state space model that you are using for this control. MPC is model predictive control, where you are predicting the future. So we can say, okay, if I follow this pattern with my control signals, my inputs here, I'm not overshooting, and I'm going to reach my goal in the future. Nice and easy. So using the model. So what I'm doing is I'm basically stimulating model, or solving an equation with current, let's say, inputs to the system. Can be more than one. Current inputs and future inputs. And so I'm solving, say, this is what I want to achieve with a cost function, and I'm solving for this use in the future. And I say, okay, if I use this use, this is the optimal solution for what I'm looking for. Yeah, again, quick introduction to system dynamics. What you have to do a lot more than this if you are doing control, but this is just an information. So what are the causes? What are system dynamics, and what are we looking at? How to solve them? We can use Laplace transform. Now we use MATLAB, of course, or Python to solve differential equation. And how they work, MATLAB does this internally. It's not of our concern, basically. Yeah, but you can program, you can solve equation like this by yourself too, in software too, using reverse Gaussian elimination or something better methods to solve the systems of equation that this state space model is.